This is the intro vid. It's designed to show just enough math to understand the music a little bit better, and then to show just enough music to understand how the math applies. The rest of the videos here go a little bit deeper into the math and music and the physics, so you want to be pretty interested to go into them. In music, the intervals go by names like octave, perfect fifth, major, minor third, major second, etc. But mathematically, it's a little bit simpler. It's simply the frequency of the high note divided by the frequency of the low note. These are the equal tempered frequencies played on guitar and keyboard, and they're selected from a continuous spectrum of audible frequencies because of the harmonies they can produce. The mathematics is a logical description of the relationship between the two intervals. When you move from low note to high note, the mathematical description is that you multiply the lower frequency by the interval ratio to get to the higher frequency. Moving from high to low, you divide the high note by the interval ratio to get to the low note. It's melody, and next we'll take a look at harmony. The G major bar chord on the guitar. And here is the G major chord separated out in chord diagram, as you often see them. This is where you put the fingers. This is the notes, the same as down here. These are the frequencies. Let me show you those. These are the frequencies. Frequencies and letter names can be interchanged. The letter names can change depending on the context of the music, the key you're in, and the frequencies always stay the same, and that's the advantage of the math. So the chord is a bunch of frequencies sounded at the same time, and they're all related by the intervals between them. The lowest two notes are separated by a ratio of about 1.5, which you could call a perfect fifth or an equal tempered fifth or simply a fifth. Depends on how technical you want to get, more technical than we want to do here. Here are the rest of the frequencies and the intervals between them. This is a perfect fourth, major third, minor third, another perfect fourth. You can get another musical interval, the major sixth, by skipping the frequency here. So all these intervals tend to hold the chord together, make it sound musical, make it sound good. These are the equal tempered intervals based on the 12th root of 2. These are the harmonic series intervals, and I'll explain them in just a second. Everything is approximated. That's what those squiggly equal signs indicate. There's just no sense trying to be too detailed at this point. The harmonic series derives from the way the string vibrates as energy is amplified by the guitar and transferred to the air. The harmonic series is an arithmetic progression where the string lengths and frequencies are related by whole number arithmetic. Equal temperament is a geometric progression where the interval ratios between the frequencies are related by a common multiplier, the semitone ratio. The systems approximate each other in the important ratios of the octave, the perfect fifth, and the perfect fourth. Temperament is a balance of qualities, and I think I can show this best on the keyboard. A musical perfect fifth is the 3:2 ratio between the first and fifth notes of a major scale, and an octave is the 2:1 ratio between the first and eighth notes. The standard piano covers a range of frequencies a little over 7 octaves wide. When you start on the lowest C on the left with a frequency of about 32.7 and continuously multiply by the 2:1 ratio 7 times, that's 2/1 to the 7th power times 32.7. Then you will get the final C on the right at about 4186. Next. The perfect fifth derives from the harmonic series ratios. Its ratio is 3:2, meaning the high frequency note vibrates 3 times every time the low note vibrates 2 times. 12 of them, or 3/2 to the 12th power, approximates 7 octaves. If they were used on the piano, the final C would be 4242. There's only one final C key on the piano, and it can only play one of these frequencies. 2 and 3 are odd and even prime numbers. They're only divisible by themselves in 1. There's no whole number solution. No multiple power of an octave will ever equal a multiple power of a perfect fifth. and no ratio from the harmonic series will ever subdivide both of them. And to divide and multiply by consistent intervals throughout the keyboard, the 12th root of 2 is used as the semitone interval. Multiples of the semitone then relate to every key and frequency throughout the musical range of the instrument. In 12-tone equal temperament, 2 to the 7/12 approximates the perfect fifth very closely. Some of the smaller intervals are not as close to the harmonic series ratios, but the logically consistent geometric progression of the 12th root of 2 takes precedence in this form of music. A modern calculator is all the proof needed to demonstrate that the 12th root of 2 divides both the octave and fifth in equal temperament. The actual proof would involve a continued fraction, but it's so tedious that the calculator is even more convincing than the proof. I do go into some of this stuff over on the Gridmath channel on YouTube. So now, both the octave and the fifth will sound the same note on the final key, and all the intervals throughout the range are related by the 12th root of 2 as a common multiplier. There are lots of other ways of making music. This is what the guitar and piano are currently using, and orchestras will generally at least try to play it when they have to. Okay, you can also think of the entire 7 octaves between C1 and C8 as a single interval, and you would take the high frequency of 4186 divided by the low frequency of 32.7, you'd get 128. And then if you take the 84th root of 128, that's shown down below, you would get the semitone 1.05946. Next, we'll take a look at a simple 3-chord progression and get an idea of the horizontal and vertical math of harmonic progression. This will show how the frequency and interval relations change as we move along in the music. These are the frequencies on the chord diagrams. The same frequencies on the musical staff. Enlarged so you can read them. Chord names and key relations. Here's the mathematical relations. And here, the mathematical and musical relations are shown for each of the 3 notes of each of the triads. The harmonic series names are used here as they often are in practice, and it's only when playing with non-equal tempered instruments like a violin that more care is taken to distinguish the equal tempered intervals. Each chord is a major triad, a perfect fifth subdivided by a minor third over a major third. The vertical or simultaneous intervals of each chord harmonize with the horizontal or melodic intervals of the progression, which is a change of chords. I thought I'd jazz it up a little bit here. With math and theory, you want to analyze an event. Music and art in general is more about the emotional impact and experience of the event. Here's some links, mostly to neuroscience.com/music, where they show how they are currently analyzing that experience. I'll put these links here down below, but things change fast.